There's an ant on this graph. It's traveling around from node to node, each time picking a random link to exit and obeying the direction of the arrows. Every time the ant visits a node, it leaves something behind and the node grows a little bit. Let's speed up the ant so we don't have to wait all day. Come on, ant. That's better. You can see that not every page is visited equally often. Pages with a lot of edges get visited more often, but also pages attached to those pages. Let's give the ant a rest and reset the nodes. Sometimes we saw the ant get stuck in densely connected bits of the graph. Other times there were nodes that the ant couldn't visit because they didn't have any incoming links. To avoid this, we can give the ant the ability to teleport. We say with some small probability that the ant can teleport to any node and set the random walk going again. While this might not be a very realistic thing for ants to do, this is called a random surfer model, and it's supposed to model the behavior of a person surfing the web. It was developed before people spent all of their time online using one of 3 different websites, but the basic idea is that the user clicks links on a web page they're on, or with some probability jumps to a new web page. Following this model for a long time and normalizing the node sizes gives you the famous PageRank score for the importance of a node in a network, which was used in the early days of Google to rank web pages. There's another way to think about PageRank. First, give every node a score equal to 1 over the number of nodes. The sum of the scores will equal 1 and that will stay fixed. Now we transfer the score of every node equally to all its neighbours. To avoid zeros, we could also keep some back and only send a fraction of the score to the neighbours. When we do this on our test network, we get the same sort of pattern that the ant generated. Either the random surfer or the score exchange results in the same equations, shown here, which defines the PageRank score for a node, which we've been representing in the animations by the size of the node. D is the teleportation probability, N is the number of nodes, and A is the adjacency matrix. Interestingly, we can do the same thing for edges that we've just done with nodes, although this isn't so common. Now, every time the ant walks along an edge, they leave a little trail behind, which makes the line thicker. Let's let the nodes and the edges grow on a well-known network called the Taro Exchange. This is a social network based on gift giving. PageRank is just one of dozens of node importance metrics. The real takeaway is that random walks are very useful for investigating the structure of a network.